Hi, I wanted to take about 10 minutes to explain one of the types of non-differentiability that we discussed. In particular, we said that if f of x is discontinuous at x equals c, then f prime of c does not exist. And what I'd like to do is to explain how this statement works by examining its contrapositive. Now that takes you all the way back to geometry when you did logical statements. And you may remember that the contrapositive of a conditional worked like this. Suppose I have a conditional if P then Q. And the contrapositive of that statement is if Q is false, then P cannot possibly be true. Why? Because if P were true, then Q is true as well. So the conditional and the contrapositive are really two ways of saying the same thing. Top, the conditional says if P is Q, then Q is always true whenever P is true. The bottom says if Q is false, then P cannot possibly be true, or Q is, or in other words, every time that Q is false, P is false as well. So we're going to use that approach to consider our type of discontinuity. We've got a conditional here. If f is excuse me, that should be labeled as P. If f is discontinuous at x equals c, then, conclusion, Q, f prime of c does not exist. So we're going to form the contrapositive of this statement by taking the negation of Q, that is, we're going to say if f prime of c does exist, then we'll take the negation of P here, f of x is continuous. At x equals c. And this theorem goes by a slogan. In fact, its name is the slogan, which is differentiability implies continuity. Differentiability implies continuity. If the derivative exists, that implies that the function is continuous at x equals c. Now let me draw you a picture so that we can see what this is talking about, and then we'll do an actual proof. And the picture looks like this. Differentiability implies continuity. Okay. So imagine that I have an f of x and I'm able to draw a tangent line so that f prime of c has some value, which is the slope of my tangent line. Then what this means is that the rate of change of f from both directions at c has the value L. And because f has a rate of change from both directions, this means, therefore, that for x's that are very close to c, f of x is going to have to be very close to f of c in order for that rate of change to make sense. In other words, x is close to c produce y values that are close to f of c. And I know this because f has a well-defined rate of change from both directions. That's the picture here. And we would say that f is smooth at c. Okay, now let's actually turn this into a proof. Here's the thing that we need to prove. If f prime of c exists, then f of x is continuous at x equals c. The way that we're going to express f prime of c exists in math is to give it a value. So we're going to start with the fact that f prime of c is equal to some value. Let's call that value d. And what we're going to try to do is to take this fact that f prime of c is equal to d and work it down to eventually the statement that f is continuous at x equals c. And I remind you of the definition of continuity. What we are really saying is that the limit as x goes to c of f of x is equal to f of c. So in all the steps of my proof down here, the very last one that I'm going to get to is going to be this guy right here. And it occurs to me that if I'm going to be talking about limits, that it would make sense for me to rewrite f prime of c using the limit definition. And so what we're really saying here is that the limit as x goes to c of all of this is equal to d. Now, to get some leverage on this, I'm going to pull off a cute trick, which you've seen me do before, and that is I'm going to clear the fractions. Specifically, I'm going to multiply both sides of this equation by the limit as x goes to c of x minus c. Just like that. Now, on the left-hand side of my equation right here, I can use the product rule for limits to rewrite the product of two limits as the limit of the product. This is using the product rule. The limit of f times g equals the limit of f times the limit of g. And over on this side, I'm going to use the constant multiple rule. Actually, no, I'm not. On this side, I'm just going to evaluate directly, because the limit as x goes to c of x minus c is simply 0. Now, what happens over here? Well, x minus c divided by x minus c is 1. So that what I get is simply the limit as x goes to c of f of x minus f of c. And on this side of the equation, that limit is equal to 0. But now, using my difference rule, I get that the limit of x goes to c of f of x minus the limit as x goes to c of f of c is equal to 0. And the limit as x goes to c of f of c is simply f of c. So that when I add to both sides, then I get that the limit as x goes to c of f of x must be the same as f of c. And all of that happens because my derivative was equal to some value d, and ultimately d times 0, no matter what d is, will be 0. Well, that's our proof. And the proof is actually useful and valuable, but the picture is even better. And that is that f has a rate of change from both directions. F has to be smooth. In other words, here's our strict legal language. If f prime of c exists, then f is continuous at x equals c. Or even better, differentiability implies